Good morning students. Now the today's topic is the Ampere circular law, and I have written the formula line negation of vector B dot vector BL is equal to mu naught dot I. Ampere circular law has importance as the Gauss's theorem has in the electrostatics. It is one of the alternative form of the Biot-Savart's law. Now let us see how this formula we can produce. This is the current carrying conductor passes through the closed circular loop, okay, and this circular loop has the radius called R. So if the current is going up, so the magnetic field going inside into the board from this point and comes out from this point. So I can denote the cross and the dot at this point. Let's see, this is called the point P. Now at the point P we will take the small element and has the direction similar to the magnetic field. So the element has the length called dl and has the direction vector dl into the board, and this is the magnetic field called vector B. And so here the vector B is parallel to vector BL. And if these two directions are the parallel, and if you want to do the product between these two, so you have to take the dot product. So I write here the vector B dot vector DL. It is equal to B dot DL. And see, if they are parallel, then they have the angle cos 0 degree. Okay. Then the vector B dot vector DL is equal to. And what about the B? The B is the magnetic field present due to this straight current carrying conductor perpendicular to the point. So the formula is mu naught by 4 pi. You should remember the formula always. It is coming I by R dot sine phi 1 plus sine phi 2. I have not discussed about the, and this DL is also here. So I am writing the DL here. And I have not discussed about the angles. See, I have told you the perpendicular, so the phi 1 becomes 90 degree as well as the phi 2 is 90 degree. So the sine 90 and sine 90 I am mentioning here so you cannot be confused. It is equal to the 90 degree. So if these two are the 90 degree, then the 2 will come. Then the vector B dot vector DL is equal to mu naught by 4 pi dot 2I by R dot DL is coming. Okay. And if you want to take the linear integration to calculate the entire magnetic field, so I have to integrate it. On integrating to get the total. So the line negation, that means we are adding all the elements. Line negation of vector DL with product B mu naught by 4 pi. Here the line negation will not affect the mu naught and the 4 pi and the current and the radius. It will increase the radius, this length DL, and the R, the integration of the DL becomes the circumference 2 pi R. So I can easily write the 2 pi R directly here. See, this 2 pi R cancels this R and the 4 pi, and again with the 2. Then mu naught I left. So this is the vector line relation of vector B dot vector DL is equal to mu naught I. So this is called also the proof of Ampere's law. Try to listen again what I did. I told you the statement, it is written here in the numerical form. The line integration of vector B dot vector DL, it is equal to mu naught times the total current passes through it. One more thing, it is valid only for the closed loop and it doesn't depend on the size, shape of this loop. I have proved the formula also, so this is called the proof. This is called the proof also. But this is for the uniform shape of the loop. Let's suppose there are another straight current carrying conductor passing like this. Has a similar direction. If it has a similar direction, then what you will do? You will write in this formula, if it has the two eyes, I am writing here directly. The vector B dot vector DL line integration, it is equal to mu naught I1 plus I2. Yes, if these two current carrying conductors carry the same direction of the current. If suppose anyone is opposite, so I have to write the minus. So the minus sign according to their magnitude, who is greater and who is smaller. So these two things keep in mind. So this is the formula. So I have to write here the plus and minus to make you understand. Okay, now I will move ahead to prove this theorem again with any non-uniform loop. Okay, so I am erasing, till then you have to note it. So this is for the uniform, I am erasing it. Let's suppose I have this non-uniform lamina, okay, and this is called the current carrying conductor passes through this point. It's called its center. I have taken this point A and the B, and this is called the point C. The length AB is equal to the DL1, length BC is equal to the DL2, okay, and the radius from O to B is the R1 and radius from O to C is the R2. And if you want to calculate the angle, then you have to draw the one line towards A. So the angle between A to B is the d theta 1, and here is the angle is called the d theta 2. So this is not the uniform structure, but I can write here d theta 1 as equal to arc upon the radius. So here the radius is R1, so I'll write dl1 by R1, and d theta 2 is the dl2 by R2. Okay. Now we have to apply the magnetic field due to this straight current carrying conductor for this element and for this element. So I'll write here magnetic field on AB. Okay, magnetic field due to it on AB, right? It is right. So magnetic field on AB is B1 equal to mu naught by 4 pi dot, because this is the straight current conductor, and I have written the formula 2I by R1 directly. And do one more thing is, if suppose I multiply the DL here and DL here, then what will be? So the B1 DL1, multiplying the DL1 in both sides, and mu naught by 4 pi dot 2I by R1 dot DL1. This is called equation number first. This practice we will do for the element CB. So you will find the B2 DL2 is mu naught by 4 pi dot 2I, the current is same for all, and the DL2 equation number 2. So you can see, and do one thing you can take for the B23, DL3, so on. I'm not going to do more than 2. So resultant magnetic field B is equal to, then do one thing, resultant magnetic field, to find the resultant magnetic field, what I have to do, I have to take the entire length of this loop. So it is not possible to calculate by apply the formula. So I'll do one thing, line integration of B vector B dot vector DL1, not the DL1, it's called the DL. This is equal to the sum of B1 dot DL1 plus B2 dot DL2 dot so on. Okay. Now apply the formula of B1 dot DL1 there, B2 dot DL2 there. So this is equal to, I am writing, so the mu naught by 4 pi is common. Okay, now mu 5 and 2I is also common here. 2I is also common. Only inside the DL1 and R1 is left here, and the DL2 and R2 is left. And for the next, if you are taking the third, then DL3 by R3, and for the next DL4 by R4 dot going to be left internally in the bracket. So into the bracket, what thing will be the DL1 by R1 plus DL2 by R2 dot. Okay. So the line irrigation vector B dot vector DL here, and the line irrigation vector B dot vector DL, it is equal to mu naught by 4 pi dot 2I. Now the DL1 by R1 is the d theta 1, dl2 by r2 is d theta 2, and suppose dl3 by r3, so d theta 3, d theta 4, dot dot so on. Now tell me, so if you are talking about the d theta 1 to d theta n, so it is making the overall angle of this circular loop, which is equal to the 2 pi. So you can write here d theta 1 plus d theta 2 plus dot dot so on. And overall angle of the closed loop of any shape always be 2 pi. So the line radiation, the vector b dot vector dl, it is equal to mu naught 4 pi dot 2I dot 2 pi by where is the r? Oh yeah, it is cancelled. Not the r is not here. Sorry, I forgot. Now this 2 pi and the 2 pi got cancelled. Again the 2 will left, then this 2 will left to cancel. So the line radiation vector b dot vector dl is equal to mu naught I. So you can prove this Ampere circuital law by using the two method. So keep note some points. The first one, the Ampere circuital law is alternative form of the Biot-Savart law. Point number 2, doesn't depend on the shape and size of any the closed loop. It is valid for the closed loop. And the third point is, what is the application of? The application of the Ampere circuital law is to find the magnetic field due to the conductor. Okay, note it down. Okay, our next topic is the application of Ampere's law. There are two major applications of the Ampere's law is given here. The magnetic field due to infinite length of current carrying conductor, and second is the magnetic field due to a long cylinder. So first I will do this, the proof of the application of the law in this first question is how to find the magnetic field by using the Ampere's circuital law. So this is the straight current carrying conductor and it is generating the magnetic field. This is called its center. This is called the radius. Okay, the magnetic field is going inside at this point and coming out. So I have to draw the cross here and coming out if the current is going up. Right? As you know, the Ampere's formula is the line radiation of vector b dot vector dl is equal to the mu naught times n the I. And if this circle has the uniform shape, so the vector b, and you can write here the dl, it is cos 0 degree, then mu naught I, because they have the similar parallel direction, and the b line radiation of the dl is equal to mu naught I. So the b is equal to b dot 2 pi r, the line radiation of the dl is 2 pi r, it is equal to mu naught I. And if I write here, so it becomes the b is equal to mu naught I by 2 pi r. Okay, you can multiply by 2 and divide it by the 2. So the same formula comes mu naught by 4 pi 2I by r. Okay, so this is the magnetic field due to this current carrying straight conductor by using the Ampere's law. Note it down. Now come to the next application is the magnetic field due to a long cylinder. Let's suppose there is a long cylinder here. Okay. And its axis is this. The radius of the cylinder is the capital R. Okay. This cylinder can be solid and can be hollow, made up of the metal sheet. Okay. And the current is passing over the surface of it. Let's suppose the point P is outside from the cylinder. Okay. So you have to imagine, as we imagine the closed surface in the Gaussian theorem, so you have to imagine the closed loop outside the cylinder. So let's suppose the outside of the cylinder there is a closed loop of radius r. Here this small r is greater than the capital R. Then you can apply the formula of Ampere's, then vector B dot vector D, a line radiation, it is equal to mu naught times under I. If suppose it has any medium, so you can write the mu, okay, and if it has only the air, then you can write the mu. So the vector B dot vector DL is equal to mu naught I, okay, and the line radiation of this DL becomes the total circumference of this closed loop, which is the 2 pi r. So the vector B and the cos 0 degree must be, you have to take, then it is B dot 2 pi r is equal to mu naught I, and this is very easy to calculate as I did in the last topic. So it becomes the 4 pi r. So it is proved. Note, it is B 1 by r. When I will write here case 1, I can write here when case 1, point P is outside, P is outside, so it will make you clear, okay. And sometimes the point P can come on the surface. If it comes on the surface, then R you can change by putting the capital R, where the field would be the maximum. And the third point is, the point can come inside. So I'll write the first here when the P is outside, I'll write here the P is on the surface. If the P is on the surface, so the formula becomes B is equal to mu naught 4 pi dot 2I by R, capital R. So this is called the maximum value of the magnetic field due to the cylinder. Now the point number third is, when point P comes inside, when P is inside. If the P is inside, so there are two possibilities. And what are the possibilities? See, as I told you, the cylinder can be a metallic, solid, either the hollow. If it is hollow, so inside there is no current. And if there is no current, so inside for the hollow cylinder, magnetic field would be 0. So I'll write here point A, if it is hollow, so the magnetic field inside would be 0. And if it is solid, the point B, if it is solid, then what would be the value of magnetic field for the point B which is inside? So there is a need to prove it. So you can note it down, and I'm erasing. Okay. See here. This is the cylinder. Again, as I told you, for the hollow it has a 0 magnetic field, and this is called its radius. If it is solid and the point P is here, and the radius would be the small r, capital R. Now the capital R is greater than small r, and you can imagine the Ampere's loop, closed loop for the Ampere's loop inside the cylinder. And what would be the magnetic field? So as we know, the current density takes very important role to prove this. Then you will write the current density for this uniform structure always be same. The current density for the cylinder and the current density passes the cylinder which can be built here always be same. Let's suppose the current density is the total current divided by total area, the pi r square, or this circular plate. And the current density for the inside, it is also equal to, so the current density I can write here, current density for inside. Say the current which is passes through the upper surface is the I, and the current which is gained by the point P inside, that's called the I dash, and it has the radius r, so the current I dash becomes the pi r whole square. At the P, the current I is not reaching, but the I dash is reaching. So these two formula, because of the uniform structure of the cylinder, would be same. So I can write here I dash by pi small r square is equal to I by pi capital R whole square. So you can cut the pi here to get the I dash is equal to I dot R square by capital R square. So this is one formula. See, now move to the next. As I did from Ampere's law, the magnetic field at this point P, the vector B, line irrigation is vector B, and the dl is equal to mu naught. Now tell me, how much current is passes through this point, the internal point P is called the I dash. So you have to write here the I dash, and the I dash has this value, so put it there. Then the line irrigation vector B dot vector dl, it is equal to, do one thing, you can, I am not writing here the dl again, so I am erasing it. Then B, the total line irrigation becomes the 2 pi r is equal to mu naught, and I dash has value this much, so I can write the I r square by capital R square, and this B is equal to mu naught by 2 pi dot mu naught I r square divided by R dot capital R. I can write here the 2, I can multiply by the 2 and divided by the 2, then becomes the 4 pi. And the 1 R will cancel here. Now the coming B is equal to mu naught 4 pi dot 2 mu I by R square, and this is small r. In this time, in the first case, when the point P was outside, then the B was inversely proportional to dr. Here, when the point P is inside, the B directly proportional to dr. So there is a need to draw the graph when point P is coming from outside to the inside, right? See the variation in the graph. Let's suppose, okay, see, this is the graph, and this is the magnetic field vector B, and this is the distance. Let's suppose R is equal to infinity, so at infinity there is no magnetic field, and if R is increasing at somewhere, R can reaches on the surface where the small r and the capital R would be same. Here the R is greater than R, and at here the R is less than R. If R is equal to R, capital R, so the magnetic field would be maximum. Let's suppose the magnetic field maximum is up to this much. And if it is inversely from this region, so the B inversely proportional to R when the point is outside, so it is increasing like this. Okay, and when it reaches up to the surface, so it has the maximum, and when it comes inside, so how much? So for the inside, the B directly proportional to R. For the inside, when the P is coming towards this axis, so the R decreases. If R decreases, then magnetic field will also decrease. So here the one proportional and straight line comes. So it is telling the B is directly proportional to R. So the graph is, here the infinity magnetic field would be 0. On coming closer, the inversely relational works, so the graph goes like this. At the surface, the becomes maximum, and when it comes inside, so it decreases continuously. And at the center, when the point P reaches at the center, so R becomes 0 and the B will also be 0. Okay? Thank you. Note it.